The question is, could you go over the derivation of the flexure formula for a beam in symmetric pure bending? You may recall this slide from one of my previous videos. We have a typical beam problem, a beam subjected to external forces and supported at certain points. If I section the beam at a point like point D and look at the internal forces, you're going to see this, right? There's going to be a bending moment MD and a shear force BD. It turns out that each of these internal forces will produce internal stresses. If I take a two-dimensional differential element around point E and mark the stresses, I'm going to see something like this. The normal stress sigma xx is produced by the bending moment MD, and the shear stress tau xy is produced by the shear force. The calculation of these stress components involve their own theories. It turns out you can calculate them separately and add them together on the basis of the principle of superposition. So in this video, our focus is developing a formula that will allow us to calculate the normal stress sigma xx as a function of the bending moment MD, along with a few other things like the second moment of inertia I and the vertical coordinate y and so on. And this formula is what is called the flexure formula. Let's first talk about some assumptions and deductions that are necessary in the development of this functional relation. Our first assumption would be that our beam is subjected to pure bending. So let me explain what we mean by pure bending. Say we have a typical beam subjected to some kind of external loading. Let's assume that we have a 2D problem, right? So if I take a cross-section at an arbitrary point, we know that cross-section is going to be subjected to a bending moment, shear force, and an axial force, right? In general, of course, it doesn't mean that all three of them will be non-zero all of the times, right? Now, if I take a small segment like this and draw the forces acting on that to an exaggerated scale like this, right? These cross-sections are going to be subjected to these three types of forces, right? Bending moment, shear force, and the axial force, like shown in this picture. If we ignore the shear force and the axial force for now, this little segment will be subjected to just the bending moment, like shown here, right? So this is what is called pure bending. So we are going to develop this functional relation assuming that we have a pure bending situation. So you might ask, what about the other two types of forces, shear force and the axial force? What are the effects of those, right? So it turns out that we can use the principle of superposition to calculate the stresses produced by these two quantities, the shear force and the axial force, one at a time again, and superimpose them. Alright, so we'll worry about it later. But for now, in this video, we're going to assume that the beam is subjected to a pure bending like shown in this picture. Our second one is a deduction. It can be deduced that the longitudinal fibers of a beam segment subjected to pure bending will deform into a circular arc. Here's a picture illustrating what we mean by saying that the beam deforms into a circular arc. Here is a beam segment subjected to a pure bending M, and this straight beam segment deforms into a circular arc like shown in this picture. In other words, this curve representing the deformed shape of this beam is part of a circle like this. O here is the center of the circle. But what is the reason that the curve is part of a circle? Here is the explanation for that. Well, the curvature is caused by the bending moment, right? But the bending moment is the same at all points along the beam. Like for example, if I take a point like point A, the bending moment on that cross section is still M. This is because of the equilibrium. In other words, this section will have to be in equilibrium as far as the moment equilibrium equation is concerned. So if this is M, this has to be M, right? So this is true for any point along the beam, and therefore the curvature has to be constant because we have the same moment acting at all cross sections. So what kind of curve has a constant curvature? A circle. And this is why this has to be part of a circular circle. In other words, the curve is a circular arc. Our third one is a deduction as well. It turns out that we can deduce that plane sections remain planes. So what exactly do I mean by this? We have a segment of a beam here, right? I'm going to take a plane on that like this one right here and mark 4 points on this. 1, 2, 3, and 4. All 4 of them lie on that plane, right? Now we're going to put a pure bending moment on this segment. It turns out this is the correct deformed shape and this is an incorrect deformed shape. So what's the difference between the two? Well, on this one, on the correct one, you can see all 4 points, right, that used to lie on that plane still lie on the same plane even after applying the bending moment, right? But in this picture, these 4 points do not lie on the same plane anymore. In other words, if I connect the 4 points like this, we end up having a curve, right? So this plane has deformed into a curve instead of remaining a plane. This is not correct. So how do we know this? So this picture will help us deduce this. I'm going to take a point like point E before the bending is applied and see what happens to the point due to the application of the bending. Say there are 2 observers here. This is observer number 1, this is observer number 2, right? Supposing, say, that point E has moved towards observer number 1. But because of symmetry, well, we have bending moment M here, bending moment M there, right? Cross section over here is identical to the cross section over there. And therefore, what observer 1 sees is identical to what observer 2 sees, right? And therefore, logic tells you that if observer 1 sees this point E moving towards him, observer 2 must see the same thing. In other words, point E must be moving towards him, right? Not away from him. So only way this can happen is if point E remains on that plane, okay? So this point E is like point 2 or point 3 that we considered in our first set of pictures, right? So I wrote down a brief statement about what I explained verbally. We're going to make one more assumption, which is the change in the lateral dimensions of cross sections due to Poisson ratio effect is negligible. So what does this mean? You guys recall what a Poisson ratio effect is? If you take a 1D beam and pull it in one direction, it's going to shrink in the other direction, right? It shrinks because of the Poisson ratio effect, right? Now let's take a segment of a beam and put a bending moment on it, pure bending. We'll see in a little bit that the fibers at the top will experience a compression. Alright, so this compression will lead to a little expansion at the top of this cross section due to the Poisson ratio effect. The opposite will happen at the bottom. The bottom fibers will extend, alright, and therefore there will be tension on those fibers. Those tension will lead to a little compression at the bottom of the cross section, again due to the Poisson ratio effect. Say this cross section was initially rectangle, so it is not going to be rectangle anymore after deformation. It's going to be more like a trapezoid, right? And this is what we mean by the change in the lateral dimensions of the cross section. So we're going to neglect this. In other words, for us, this rectangular cross section remain a rectangle even after deformation. Now, what are the consequences of the assumptions and deductions we have discussed thus far? Number 1, these assumptions and deductions lead to the conclusion that pure bending does not produce shear stresses. How do I make this conclusion? Say this is a beam segment before the application of the bending moment. I'm going to draw a rectangular grid on the side elevation of this beam. This is how the beam is going to deform, and then the rectangular grid is going to deform like shown in this picture. So what is so special about this particular pattern of the deformation? In this rectangular grid before deformation, all these are little squares, right? So what happens is all these little squares deform into what we call curvilinear squares. So these are curvilinear squares. What that means is these corner angles are still 90 degrees. And this is true for every little square that you have in this rectangular grid. How do we make the conclusion? Well, this conclusion comes from the two deductions that we have made earlier. These longitudinal fibers remain part of circular arcs, right? That's number one. Number two, these plane sections remain plane, all right? So these are the reasons why these are curvilinear squares with 90 degrees at the corners. So the corner angles are 90 degrees before deformation, and the corner angles are still 90 degrees after deformation. So that means there is no change in these angles, right? So remember the definition of the shear strain, right? So the shear strain is the change in these angles, right? And therefore, we don't have any shear strains. That leads to the conclusion that there are no shear stresses. There is no shear stress on the face or any cross-section on the beam. The second consequence leads to the formula that we are looking for. In other words, we are going to be able to derive a relationship between the normal stress sigma xx and these variables. We're going to be using this picture to develop these relationships. Let me first define my coordinate system here. X-axis is taken along the length of the beam. Y-axis is perpendicular to it, like shown here, and the Z-axis is perpendicular to the board here, or paper. We will restrict our analysis to the case where this cross-section right here is symmetric about this axis, Y-axis. Remember what we said a little earlier, right? If you put a pure bending like this, right, the fibers at the top of the beam is going to be shrinking, and the fibers at the bottom of the beam is going to be expanding, right? So that tells us that between the top and the bottom, there has to be a fiber that does not undergo any deformation. Actually, it's a surface, right? This is the surface on the side, and this is the surface on the cross-section, right? This surface is what is called the neutral surface. On this is called the neutral axis. In other words, the Z-axis over here is the neutral axis. So the length of the neutral surface does not change. In other words, there is no strain on it, right? So we're going to place the origin of the coordinate system on that surface. But we don't know exactly where that is yet, but we will find out in a second. Again, recalling all of these fibers deform into circular arcs. Let's say that the radius of the arc that the neutral surface deforms into is rho. This angle right here is theta. Now we are going to consider another fiber shown by the dotted line right here, and this is at a distance y from the coordinate from the origin. Since the fiber DOE, that is the fiber representing the neutral surface, does not undergo any deformation, right? The original length of this fiber right here is exactly equal to this, right? That is because all of these longitudinal lines had the same length originally, right? That is before we put the pure bending on it, right? Now we can see this fiber represented by the dotted line has shrunk a little, right? So it has become smaller. So let's go ahead and calculate the strain on that. Remember, normal strain equals the change in length divided by the original length, right? So here's a little analysis that I have done, which led to this relationship for the longitudinal strain epsilon xx. So this is what I did. The original length of jk, right, this one right here, is exactly equal to the current length of the neutral surface, right? So this length right there. And since this is a circular arc, the length equals rho multiplied by theta, right? So let's say, let's call that as L. The current length of jk, right, is the current radius of that, which is rho minus y multiplied by theta. Let's call that as L prime. So the longitudinal strain on the fiber jk is simply the change in length divided by the original length, right? So that leads to this little expression here. And of course, here I am taking the tensile strain to be positive. So let's analyze this equation we just got a little bit more. Since rho, which is the radius of the neutral surface, is a constant, what this equation tells us is that the longitudinal strain epsilon xx varies linearly with y, right? It is 0 when y is 0. So if I were to plot this as a function of y, I'm going to get a straight line like this, right? And this straight line has a zero value here, and the maximum compression over here, and the maximum tension over here. At this point, we're going to assume that the material behaves in a linear elastic manner. In other words, the stresses are small enough that we are in the elastic region, right? And therefore, there's a linear relationship between the stress and the strain, and the constant that relates the two is what we call the Young's modulus, right? And therefore, stress varies linearly as well. In other words, the normal strain on this fiber, right, varies linearly with y. You have zero stress on the neutral axis, maximum compressive stress on the fibers at the top, and the maximum tensile stress on the fibers at the bottom of the beam, right? Now, with this understanding of the way the strains and stresses vary across the cross-section, we're going to apply equilibrium in order to link these quantities. So, first equation is a force equation. We realize that what we have on this cross-section is a pure bending, right? We are not applying any axial force, right? And therefore, if I take this stress, normal stress, integrate that over the cross-section, right? And that should be equal to 0 because there's no net axial force on that cross-section, right? So that's what I'm doing here. So I'm integrating the stress with respect to A, the cross-sectional area, right? And then I'm utilizing this equation right here in order to simplify this. So sigma xx is this, and I bring this and put it in here, and these are constants. I could pull them out of the integral, right? So that leads to the conclusion that integral of y times dA must be equal to 0. Have you seen this before? Yeah, this is how we evaluate the centroid, right? Remember, this is the first moment of area. If the first moment of area is 0, that means this point is the centroid of this cross-section. Remember, we didn't know where the neutral axis was, right? Now we know. The neutral axis passes through the centroid of the cross-section, all right? The second part of our equilibrium analysis is to express the bending moment that we are applying on this cross-section as a function of the stresses. If I take a little differential element right there, right, multiply that by the stress, what do I get? I get a small differential force at that point, right? Say I want to take a moment of that force with respect to the z-axis, which is the axis perpendicular to the paper, right? So what do I need to do? I need to multiply that force by this distance, right? Y. Okay, that's what I have done over here. Sigma xx times dA is my little differential force. Multiply that by y, I get the differential moment, right? And if I integrate that over the cross-sectional area A, what should that be equal to? That should be equal to m, the moment that is being applied externally on that cross-section. So that's the fundamental idea. All of these are details. So now I use equation number 2 to express sigma xx in terms of y. That's what I have done over here. Again, this quantity can be pulled out of the integral because these are each parameter in that expression is a constant. Do we recognize this quantity? Remember, that's the definition of the second moment of inertia, right? And that is the second moment of inertia but the z-axis, right? So let's denote that as I. Now once again, using equation number 2, we know this quantity right there minus E over rho is simply equal to sigma xx over y, right? So now I'm gonna substitute this for this quantity and I get this. In other words, sigma xx equals my over I. This is what is called the elastic flexure formula. So finally we have the equation we've been looking to derive all this time. So here's a little summary of these equations. The normal stress at any distance y from the neutral axis is given by this equation. Sigma xx equals my over I. Now if I'm interested in finding the maximum compressive stress, all I have to do is to use C1 for y, right? So that's what this equation is. And similarly, if I'm interested in finding the maximum tensile stress, which is going to happen at the bottom of the beam, right? All I have to do is to use C2 for y. So C2 is the distance measured from the neutral axis to the bottom of the beam. Now if I want to calculate the strains at any of these points, all I have to do is to take the stress and divide that by the Young's modulus. So now we have simple practical equations for calculating the stresses and strains. So here is a schematic representation of the normal stress sigma xx at a point like point A, right there, okay? So this gives you a complete picture of what's happening at point A. You can see only component that is non-zero here is this sigma xx, alright? Sigma yy is 0, sigma zz is 0, and earlier we showed that there are no shear stresses, so we don't have any shear stresses on any of these faces. So this is what the pure bending does. Also just keep in mind that we have compressive stresses over here and the tensile stresses over here because the bending moments are acting like this, right? If I reverse the direction of the bending moment like this, right, then we're going to have tension over here and the compression over here, alright? I want to introduce one other terminology here. In the earlier slide we saw that the maximum stress, either a compressive or tensile, occurs at the outer fiber of the beam, right? For example, if this distance is c, then we know the maximum stress is given by this equation, sigma m equals mc over I. And in the expression on the right side, we notice that this part right here, c over I, is simply a property of the cross section. This ratio right here, I over c equals s, is called the elastic section modulus. The bending stress, the maximum bending stress, then can be expressed as m over s instead of mc over I. Earlier I mentioned that in this course we'll only consider sections that are symmetric about the y-axis, right? But we never talked about what exactly does it mean, right? Well, it means two things. Number one, the centroid of the section lies on the y-axis. Remember we learned this before, right? If there is a line of symmetry for a cross-section, the centroid is going to be on that line of symmetry, right? So this line happens to be the line of symmetry for this cross-section and therefore the centroid is going to lie on that axis. In the problems that we are going to be looking at in this chapter, we are going to assume that there is only one bending moment. Remember in general there could be three components for the bending moment, right? There could be one about the x-axis, one about the y-axis, one about the z-axis, right? So the one that acts about the x-axis leads to the torsional problem we looked at earlier. So here we're going to assume that's 0. We're also going to assume that the bending moment about the y-axis is also 0. So the only non-zero component of the bending moment is mz, the one that acts about the z-axis, the one that is perpendicular to the paper, right? So we'll simply call that as m, right? What this means is that the normal stress sigma xx does not vary in this direction. This is the z direction, right? It doesn't vary. In other words, the distribution of sigma xx in the z direction is uniform. So that's what I'm showing here on a line from A to B. So the normal stress varies in this direction, but not in this direction. Because the stress is uniform in this direction, now if I take a little differential area like this, and integrate the force acting on that, right? In order to find the bending moment about the y-axis like we did before, but this time using a moment arm of z in this equation, it's going to turn out to be 0, right? Which is consistent with the fact that we don't have an externally applied moment about the y-axis. This doesn't mean that this is always the case in practice. In fact, you could have a non-symmetric cross-section. Theory for this case is covered in the book in the section on unsymmetric bending, but it's beyond the scope of this course, so we will not get into this here.